So first of all, why such a title? Well, there are various ways of, you can think about learning models or why they make them interact. So the first one is you might just use different models to learn something about the uncertainty that implied by these various models. And that can give, I mean, you can do this by making them interact. We will see this. Maybe a bit more fundamental is that that you want to make them interact so that overall they follow some sort of path that could be an observation or some process you want to track or something of this sort. That's actually my primary interest, which comes from sort of metrology and data assimilation. More generally, this has become pretty popular. You make them interact to solve some Bayesian inference problem. I mean, we heard, for example, our minimization problem. Eric van Nijden talked about this on Wednesday morning. And you can think of them, I think they're attractive. Some of them you can see as derivative-free methods. So the interaction sort of approximates derivative in a way, but without explicitly computing them. So it's becoming a pretty popular field. And then you can also think of them from more like a game theoretic point of view, that you make them interact to maximize some rewards, and then you're getting sort of into optimal control, sort of particle representations of optimal control laws, or reinforcement learning, things like this. So to get a bit more specific, before I do this, the main ingredients of my talk, I mean, we have interacting particle filters, so there will be mean field equations, like in Greg's talk earlier today, and there will be interacting particles, obviously. I think the particular twist I like, that's sort of my favorite, is to link all this with couplings and optimal transport and things like this. So this is my personal take on it, and I will show you how to make use of this. All right. Okay, so as I said, I come primarily sort of from weather forecasting, and so they actually have sort of interacting models, or they have interacting realizations of a model. So so this is I took this from the ECMWF, which is in Reading around the corner. And so basically what they do, they have ensemble prediction systems where you have a model, and I just take it here as an ODE. It's really a discretized PDE, but in the end it is becomes an ordinary differential equation of huge dimension. And there's an uncertainty about the state, and then they produce various forecasts, which are shown here. These are geopotential fields. And that is then used, I mean, they typically have sort of about 100 of these realizations. And then you get these spaghetti plots, which show you a little bit where the fronts could be potentially over the range of the next 4 days or 10 days or something on that scale. And then the next step is that you actually not just do like this model, but they do some augmentation to it. So there's on a sort of a bit of a simplistic, simplified level, there's a blue and a red addition to the system. So this is sort of the forecasting system on its own. Each model, I is sort of a realization, if you think Monte Carlo, of your forecast, and you propagate this forward under the dynamics. And then they have this term, which they call inflation. And that's there to increase the spread somehow, because they don't quite trust the model, so they say, well, the spread, I mean, the coverage of the possibilities might be too small, so they add this term. It's important that the sign is plus here. So in Greg's talk, there was a minus here. And here, this is the mean, right? So this is the empirical mean over all the forecasts at the time. So that leads to a very weak form of interactions, just through the mean. And because of the positive sign, it means that the things separate. It's destabilizing, and then of course you can ask yourself, what are these? The alpha is a coefficient, the q, we will see what that is. So that's one thing that's used. And then there's another term that basically to produce meaningful forecasts, you always have to align with observations. So y is some data, and if it's like precipitation data, these are radar images. and they come in very high frequency, so you can almost think of them time continuous. And then you compare your your observations with what your model would produce. So H is the operator that links the model variables with the observation variable. So in this case, it's called latent heat nudging. So that would be latent heat. And so you compare these two things, and then you nudge this via a coefficient k onto the dynamics. And again, the question is how to choose these things. And we'll discuss this. So these two additions are important. And I want to now motivate these things from a sort of mathematical perspective. And they will lead to interactions of various forms. So let's start with the inflation bit. For doing so, we make a little jump. So we have seen SDEs a lot of time. The only addition here is this plus, because I will go forward and backward in time. So for now, we go forward in time, which is sort of the standard regime. So here's a drift, and now I add some noise to it, diffusion. I think that should be pretty clear. The initial distribution is the initial uncertainty in your model. And we all know that this generates a measure. If we look at a time interval 0 to capital T, that gives the solutions generate this probability measure. Now, one thing I'm going to use a few times in my talk, that you actually can go backward too, right? So with an ODE, of course, we can just go forward and backward. With an SDE, things are a little bit more tricky. So basically what we want is that if I take the density that this forward model generates at final time t, the marginal, then I want to have an SDE that I solve backward in time from capital T to 0, and then I end up with this distribution. And how do I get such a model, or backward SDE? Well, I have to use backward Brownian motion. That's why I have the minus here now. And I need a drift term that does the job. And it turns out, and on the next slide I will show you, it's actually quite easy to see why this term comes into play here. So this is original drift, and then this is the correction. And that correction itself involves the marginal densities that the forward dynamics has generated. So that clearly is now if you think of this eventually being discretized, this is like a mean field equation. Also, it requires knowledge of the whole density. It's not just a single forward shooting you do with this. Where is this term coming from? Well, you look at the Fokker-Planck equation that describes the evolution of these marginal densities. Now here's a plus. You have to convert this into a minus to account for the backward Brownian motion. And of course, the equations have to be the same, right? We want the evolution equations in the marginals remaining the same. So you have to shuffle the difference into the B or add it to the F. Now you can push this even further, and you can say, I don't like diffusion at all. I don't like any noise. So I shuffle everything into something that looks like advection. So I get a modified drift term, which is the average of F and B. And then there's no diffusion at all anymore. You have to reinterpret. You did reinterpret this as a drift term. And so you end up with a mean field equation, which is now deterministic, but again involves, even if you solve it forward in time, involves the unknown marginal distributions. So, and again, if you discretize this, then you get an interacting particle system. Now, what does it got to do with this inflation business that the meteorologists use? Well, if you make a Gaussian approximation here, you assume your distribution is Gaussian, then the log, of course, gives you a quadratic term, the inverse covariance appears, and the difference of each forecast minus the mean. So this exactly of the form of the nudging that meteorologists use. So this is the Q. Now in meteorology, the Q is actually Yeah, so this is actually a form that they really use in this inflation. This is then estimated empirically from the ensemble members you have. And the alpha is the strength is sort of the gamma of the diffusion. So even though meteorologists in a way don't like stochastic models often, I mean, if you talk to them, they say, well, I don't really like this SDEs. I mean, we trust our models enough to not. But in fact, they do this, right? I mean, it's just that they represent it differently. They use it as an inflation. And it's essential to the business. I mean, they really need these terms to make it all work. Okay.
Does it depend on capital T?
Capital, no. You mean this? No. It just requires the marginals, right? So you propagate your ensemble or your Monte Carlo samples forward in time, and you use this to estimate this by assuming that this is Gaussian. So it's not a boundary value problem. It's still forward in time.
But I thought you were conditioning on the pi at time capital T? Or
No, well, this was when I said I would do the backward equation. Now I'm actually the meteorologists go forward in time. The backward equation will only be for theoretical purposes later on. That's why I introduced it at this point. So what I'm using is this form now here. So I don't use this. I use this to replace the forward model by this model. So I have the forward SDE, and I reinterpret the forward SDE as a simple or an advection with this modified drift term.
Can you summarize what is it doing now, actually? What is the purpose again?
Well, the purpose is meteorologists, or we want to characterize the marginal distributions of this variable at time t. Right? So then you can solve the SDE, or you can solve this system. In terms of the marginals, it's completely equivalent. Not in terms of the path measure, because this is now a deterministic equation. The equation solutions are smooth. Just the marginals. You just want to reproduce the marginal distributions at time t for all t, from 0 to, let's say, capital T. And so what we've done, by this reformulation, we have eliminated the stochasticity. Instead, we have to approximate this. But if you do a Monte Carlo method anyway, then you can approximate this, and you can, for example, use a Gaussian. Or some other, you could use some kernel method. But what the meteorologist implicitly assuming if they do this kind of inflation is a Gaussian approximation. And that's not too bad, I mean, in many applications.
But you have to choose gamma.
The gamma, yeah, I mean, this is, yes, so this is still a heuristic thing they tune somehow. Right? So.
Because, I mean, they say it's not probabilistic, but it's exactly the amount of noise. So.
Yeah, sure. So this, well, if you were to start from an SDE and you know the gamma, then fine. But they, as I said, they don't really like to think this way. But then for them, it's a tuning parameter. And they call it inflation parameter. It is and they have an adaptive way to estimate it. I mean, they have lots of data, so they can really check how well their forecasting system works, and then they tune the parameters accordingly in a heuristic way. Okay, so now the idea I just showed you actually shows up in other things as well. For example, there's something that's become popular. This is the Stein variational approximations. I mean, I don't know if you've seen it. There's a couple of archive papers. So basically, my perspective on this is that it's, again, it's sort of a deterministic way of minimizing the Kullback-Leibler divergence of some of the prior, and it evolves in time to approximate the posterior distribution. So you can, of course, do it via an SDE, right? So this is the posterior distribution conditioned on some data. You start this SDE with the prior distribution. It will asymptotically converge to this distribution. This is the invariant distribution, right? But if you don't want to do this, you can do the same trick I just used before. You can reformulate this problem as Felix Otto's framework as a gradient flow on Kullback-Leibler. And then you can discretize it using Monte Carlo, and then you get basically an interacting particle representation that in principle does the same thing. And then you can continue this and do maybe further tricks to accelerate convergence, etc. So of course it's not per se clear why such a thing is better than this thing. Of course, this being deterministic, it will at some point hopefully equilibrate and then not giggle around anymore, whereas here of course you still have sort of a moving particle system, but it will be from the right distribution asymptotically. And you can also use this for variational base. I mean, you can say this is in a certain class, I mean, a reproducing Corner-Hilbert space, for example, and you find the best approximation to the posterior in that class, and things like this, all right? Anyway, so this is exactly the same idea. It's the same principle. Replace a stochastic SDE by something that's interacting.
But if you start from a Dirac initially with a deterministic...
No, this you can't. No, this no, you can't do this. No, this
You
doesn't.
really need some
Yeah, you
time.
need some smooth initial. I mean, otherwise, no, you can't initial. No, that kills you. Yeah. No. So you have, so you need something smooth here. Yeah. Okay, so some references. This forward and backward stuff is Nelson. It goes back to the 60s, maybe even before then. And the Stein variational, which I referred to, is one of the archive papers, is this down there. And then there are a couple of books on data assimilation, and of course, Pierre Desmoral. Anyway, so this takes care of the diffusion. Now the next thing is, where do we get this term from, which sort of links the model to the available data, and which looks like nudging. Now, a mathematician's point of view, you like to have a likelihood somehow. So so some cost functional, which will depend on some function v. In our case, it will be a discrepancy between the data and what the model would say the data should be. And I simply take the 2 norm here, and again some strength, which is related to the measurement error in a way, the inverse of it. But this could also be something else. I mean, this could be that you want to simulate a rare event, so it could be something attached. It could be a reward function. It can be something you like, right? Or you like to you like to inform your model about. And informing the model about is saying we do Bayes' theorem, and we take the original measure generated by the dynamics, and you want to have the one that's generated by the Radon-Nikodym derivative with this likelihood. And if it's an SDE and this would be a stochastic, a random observation, then it's the classic filtering smoothing problem. But I will actually for now assume that these observations are smooth in time. Okay, so now we're going to play again. It's sort of playing the same game again. What we're going to do is to say we again look just at the marginal distributions of this desired posterior measure. And we want to again generate an interacting particle system so that it agrees with this object marginally, not as a path measure, but just marginally, because that's typically what at least meteorologists are interested in, and in many applications that's good enough. And so how we go about this? I'm not going to give you the details, but ultimately there are various forms. It's not a unique. I mean, you can do it in many ways. But one way to do it is you find a potential, which itself is the gradient of is a solution of an elliptic partial differential equation, where the covariance matrix, the second moment of P of the desired marginal distribution appears. And again, the distribution itself also appears. I could take that out. I leave it in for the next slide because it leads to some nice result. And on the right-hand side, it's what appears in the cost function and the likelihood minus its expected value, right? Because the expected value of this side has to disappear so that this has a solution. So again, this is now a much more complicated interacting particle system because it's actually the interaction is implicitly defined. But it has a property that exactly produces the marginal. So it's a right control term. Now again, how is that linked to what meteorologists do? Well, again, Gaussian. So if this operator is linear, and if the distribution, again, is assumed to be Gaussian, then you can actually solve this elliptic problem. You have a closed form solution, and it is of this form. And if you compare this, what nudging would be doing, it's actually interesting that there's a slight difference. Nudging compares the observation with what the model would say. And then there's a nudging strength. And here, the innovation, what control people would say innovation, is actually you compare, interestingly enough, the average of the predicted plus the predicted mean. And then you take this. And also, you find that the nudging coefficient is flow dependent. It has the covariance matrix, so it has a second order moment and the operator H transpose. And if you look at this, it looks very much like the Kalman filter gain, the Busse-Kalman filter, time continuous Busse-Kalman filter. Now, this form is very important. If you do this, then you can show that you underestimate this, that it's contracting the distributions too much towards the observation, which means that the uncertainty is underestimated. So you need inflation to correct for this. If you do this, then everything is consistent with the Kalman filter. If the system is linear, the Gaussian, all the distributions are Gaussian, you can show that this is actually exactly equivalent to the Kalman-Busse filter from the 60s. Now, meteorologists also use this in the nonlinear context, and it works again quite well. But in principle, this is the framework that you need to think about if you want to go beyond this Gaussian picture. Right. So now here's the whole system now discretized. So this is now a good sort of data assimilation system for the meteorologists. So this is the nudging that's coming from representing the model error. And this is the Kalman-Busse part, essentially, with a flow-dependent gain and innovation also being flow-dependent. And so you get an interesting sort of interacting particle system. Now, I've been working here with the observations being smooth. You can do the standard model for observation is an SDE itself. You can do this as well. So then this cost functional term that in the cost functional, this one you have to replace by this expression, and you get the Kushner-Sakai equation that you need to that the marginals satisfy, and you need an interacting particle system that reproduces the marginals of the Kushner-Sakai-Stratonovich equation. And you can do this, and it has been done by Sean Mine and Prashant Mehta. And it's a beautiful result in the sense that this whole framework still goes through, except that this the gain, again, has to solve an elliptic partial differential equation. So, but it looks like Kalman from the 60s, plus that it's now general and applicable to all sort of non-Gaussian cases. It's just that you need to change the gain. Okay, again, some references. So this is all on reformulating sort of homotopy type things where you want to transform one distribution into another. Jürgen Moser did this for theoretical reasons for many years ago. And then from the data assimilation perspective, Fred Daum and myself, and then the Kalman filter stuff, and then, as I said, the feedback particle filter of Sean Mine and Prashant. It's also interesting, we started doing some work on, if you look at these particle systems, of course, you like to show some sort of stability and accuracy results, right? You want to show that this is not blowing up, and you want to have some mean field limits. You want to show that the mean field limit is the correct one, et cetera, or that there is a mean field limit. And in this publication here, we shown this when the measurement errors are assumed to be small, so the limit of small measurement errors and fully observed systems. So it's not a very interesting application type scenario, but it's the first sort of theoretical result where you can show something. Okay. So this is the time continuous. Now, if you go time discrete, you have observations of this time. So at discrete points in time, Tn, you have the same sort of thing plus measurement error, which are now Gaussian distributed, and with an error, measurement error covariance of R. The likelihood is then the integral becomes a sum, this quadratic thing. Again, what we really like to know about is this distribution, which is the filtering or smoothing problem. Now, what I'm talking about is not tied to the fact that this comes from observations. It could be, again, that you do trying to do some rare event simulations. Could be that there's some reward that you get that's not related to data, but some other things. But anyway, so we want to, again, get an interacting particle system that represents this distribution. Right, and because I think sequentially, I want to do this going from time 0 to time capital T in a sequential manner, reproducing the marginals of this distribution. Again, not the whole distribution, just the marginals. Okay, so we just need to look at one interval. So the likelihood, the log likelihood function becomes this. I set R to the identity. The time is so it's just a single step. Now the thing becomes a little bit more tricky because we now have a few more players. In the time continuous case, a lot of things collapse into one object. In the discrete case, what you do, you have your sort of last analysis. I mean, the last thing you estimated, seen all the data up to that point. And the meteorologists call it an analysis. So this is the marginal at some point here. And I start with 0, but it could be any time in this interval. So that's what I have. I assume I have done this somehow. So then I have a model, an SDE, that propagates this forward to the next observation. So this is then the prior at the next observation. So again, you can do Bayesian analysis at that point, and you get a posterior at capital T. So this is where you want to get to in a way. And of course, having the prior at this time, now I can actually go backward in time with my backward SDE and say, what is the distribution, corresponding distribution at time 0? So this is the distribution that's seen the data at time t already. So it's a smoothing distribution in this called, right? So these are the 4 players. Now, the standard way of going about approximating this is you take this, you use your model, go here, and then you have a discontinuous change from this distribution to this distribution, and you do resampling or you do something, but it's still a discontinuous change. It's not dynamic, so it's an artificial step. And what we really want is some sort of dynamic reinterpretation as an interacting particle system. All right? So we've seen this example this morning already, the double well potential. And I assume that at time 0, the mean is here. I mean, so I'm in this well, and I mean, my distribution is basically concentrated around here. So this is my initial distribution at time 0. And for some reason, the next observation tells me that at time t, the solution is over here, or at least somewhere over here. So that's I have to shuffle somehow the particles over there. So now what if I, with this particular setting, so this distribution just under dynamics, the forecast, I mean, there's this little tail that hops over it, but most of the particles are still here. And then the analysis which I obtain combining this with the observation, and the observation error is not too large, it's that it should really be here. So this is the posterior distribution at time capital T. And this is the smoothing distribution at time 0. So at time 0, the smoothing distribution looks a little bit like I'm not quite decided whether I should be in this well or in this well. And as I said, the traditional way is you do this, you go here, and then you go down here. Of course, in particle filtering, people already many, many years ago figured out, okay, you can also try to do this. You know how to get from here to here. I will show you in a minute. It's an optimal control problem. So then you go from here, you jump to this, and then you have a dynamic propagation to go from here to here. Now what we're going to do today is actually going straight from here to here. So we're going to try to find a control that gets us right from here to here. But let's do first this avenue, and that will show you then, guide us to how to get straight from here to here. And that's where this forward-backward stuff comes in. So the forward shooting is sort of you start with your last analysis, and you just solve the forward equation. That gives you your forecast at any time, up to capital T. Then you use your backward SDE, but you start your backward SDE actually with the posterior distribution. So that's the one distribution that has seen the data. So you start not with the P at capital T, but the one that has seen the data, the posterior distribution. So you go backwards. And that gives you the smoothing distribution. That gives you the distribution that has seen the data. But you can think of this as solving this SDE backward in time. Of course, you could also do the backward Kolmogorov equation for the ratios, but let's think of it, because we like to think particles, it's nice to have an SDE to begin with. And then if you want to do the step from here to here now, you get yet another forward SDE with a correction term. This is a control law you have to add to get from here to here. And you initialize with the smoothing distribution at time 0. You solve this SDE forward in time now. This is backward in time. This is again forward in time. And that gets you to the filtering, the filtering or smoothing distribution at capital T. OK, but and that leads to what's called in particle filtering the optimal proposal, or the optimal control, etc. OK. Now, as I said, we really go from here to here. How are we going to do this? It's just a little tweak to the story. So we're going to say, try to find the measure that minimizes the Kullback-Leibler divergence, and we heard the notion of Kullback-Leibler a few times already, with respect to the path measure of your underlying SDE model. And now we formulate the whole thing as a boundary value problem. We say that we want to that all these measures here satisfy the distribution P naught at time 0 and the filtering or smoothing distribution at time capital T at final time. So we formulate the whole thing as a boundary value problem over path space. And that's called the Schrödinger problem. Schrödinger did this in 1931. He published a paper on this where he basically posed it as a problem.
Not only the time marginal, it's really the path.
This is here the whole path, yeah. But it's not going to be 0, right? So so if this was the smoothing distribution, if I would put in the hat here, then it still would not be 0. So you're finding a different bridge. Of course, yeah. So this is really now this is really the whole path. And again, it turns out that this can be generated by an SDE. It's not surprising that it has to be absolute continuous with respect to the original SDE. So the only thing you can really change is the drift, and that is sufficient. I mean, you can do it. And so again, it's just a question how you find this control. And so again, it turns out you have to. I mean, the one way to look at this is this forward-backward SDEs business. But now we have sort of the setting is. I mean, it's basically like the smoothing problem. It's just that the boundary conditions are a little bit different now. So you start with an initial distribution I call with 0, and it's the distribution I propagate under the forward SDE. For the smoothing problem, remember, this was the P naught. This was the last analysis, or the distribution at time 0. So now we're looking for a modified initial distribution, which we propagate under this model and up to capital T. And then we have, again, the backward SDE, which defines a control or correction term from this distribution. But this is now not known. It's sort of part of the problem to compute this. And you solve the backward SDE from the known posterior distribution of capital T. So this is known. And you shoot backward. And the goal is that this is chosen in a correct way so that you end up at your last analysis. And then the optimal control is again the ratio of these two densities, obtained from the forward and the backward SD shooting. So now this is a full nonlinear, this is a full boundary value problem now. So the smoothing problem is a simplified version where you just need to go forward and backward once. You can think of the Schrödinger problem as you have to go forward. If you think of boundary value problems as shooting problems, then you go forward and backward and you do it till it converges. Yep.
I think I got lost, but you said the little phi sub little t.
Yeah.
That you don't know.
Well, this is determined by the boundaries. I don't know it a priori. In the smoothing problem, I know it a priori because I know this is at time 0. This I know.
So that's the marginal of the z.
Yeah. So this is now part of the unknown.
That's the law of the z minus t.
Yeah. No, this is the law at time 0 of the positive, the forward SD.
Right.
But that law at time 0 I don't know anymore.
Right.
Instead, I know the two laws of the backward distribution. But to know that, I need to know the plus. So implicitly, it's well defined, but it's no longer explicit. So it's a boundary value problem. And you shoot forward and backward, and it gets something that if you know the synchron iteration, it's basically a type of synchron algorithm. Okay, so you can implement this. The way, again, I did this for this particular problem, I approximated these by Gaussians. So I didn't look into the space of all distributions, but I used Monte Carlo methods to sample from these distributions, and I fit a Gaussian to it, and that gave me an approximate control law. And I did 10 iterations, and so you see it's not perfect. At time final t, the controlled posterior, the one that I get by solving this controlled, finding the control law from the Schrödinger problem gets me here, whereas the real posterior is a little bit further to the right. It works okay. So just to summarize again, this difference in the boundary value problem. So for the smoothing, if you think the plus, this is given, so I can go forward in time. For the backward, I also know I know the boundary condition for these two problems, so it's easy to solve. Whereas here I have the boundary conditions on the distribution that goes backward in time, and I don't know the one for the forward in time. It's part of the problem which I need to solve. Now, if I assume, which you have in particle methods, that you actually only have samples from a distribution. Like if you think of sequential Monte Carlo, all I have are samples. I never have a distribution except for my samples. So all I have is this empirical distribution. So then finding this distribution, then this is also empirical. So you just have to actually find m numbers. So you can write this as a fixed point iteration in these m numbers, and that then really is a synchron approximation, which I'm not going to go into this, the details of the synchron approximation. It's sort of essentially a discrete version of this boundary iteration, forward and backward shooting. The difficulty is not quite as simple as standard synchron, that at the other end, of course, you have distribution, so you need to compute expectation values with respect to this distribution at the other end. So you have to do an approximation there. That's why I talk about these stochastic algorithms there to approximate that. Okay, whoops. So again, so originally it came from Schrödinger. Then there are two nice. This is a very nice paper if you want to learn about Schrödinger bridges and control perspective. I highly recommend this one. A more mathematical one. I didn't cite it here. There's one by Leonard, Christian Leonard, French. It's more mathematical. And then there's also a very nice book now, or this is a draft book by Mark Couturi, on computational methods for optimal transport, where they also talk about the synchron. So if you like to learn about these numerical methods about transport problems, that's a very nice source. And I'm writing on an Acta Numerica paper where I sort of put this into the context of data assimilation, so what I talked about. So, how are we doing time-wise? How do you feel?
There.
Huh?
We're pretty much there.
Okay, I think that's good. Yeah. So I have a few more slides, but I'm gonna save you with this. So in a nutshell, let me just the summary at least. I talked primarily about data assimilation, but in a way, whenever you want to learn something, meaning that you have a change of measure, the learning as a change of measure, then there is one way to think about it is you set it up as an interacting particle system. A change of measure per se doesn't tell you how to do this. And to define dynamics, you need to couple measures. And so I think the Schrödinger, or the optimal transportation problem, if it's deterministic, is in a way, optimal way of coupling two measures. And once you have that coupling, then you have a dynamics. Before, typically learning doesn't tell, if you think about interacting particle systems, learning is then, from a Bayesian perspective, all about marginal distributions. It doesn't tell you how you actually change particles that represent this, or how this leads to a dynamic. So coupling is essential for going from some sort of learning problem to an interacting particle system. Well, of course, numerically, it's mathematically, I think I really like this optimal coupling transport stuff tremendously. Of course, computationally, it's a bit of a headache. But actually, stochasticity helps you. Yeah, so it's relevant for all sort of things. As I said, there's a lot of interest now in deriving very efficient derivative-free optimization problems. And of course, all this is tightly linked to optimal control. And here's the list of collaborators. And I thank you. And I think I'm the last speaker, am I? No? Yeah. Okay. I guess Ben set it nicely up in saying, let me thank me first. But I think we should all thank Ben at this point. I think he done a tremendous job of organizing it. I unfortunately had to miss a few talks because there was another meeting colliding with it. But from what I hear, it was excellent. So, yeah.